This is 8.5 for Math 31, where we look at exponential growth and decay. What we're going to use in this particular course is going to be a little bit different than what we used in Math 30, where we did, to the power of something. Really what we're looking at is that certain quantities grow or decay at a rate, I'm reading here, that's proportional to their size. And if you think about population growth, the rate at which, our population grows changes as there's more or less humans, because there's more or less people available to reproduce. And that's a really important consideration, that when we talk about true exponential growth and decay, the more elements there are in the population, the bigger, or the faster, I should say, that population is going to grow. Now, in calculus, we identify that as the derivative is equal to k times the original function. A lot of this is looking at, if you take more calculus courses, you'll get into this in a lot more detail. What we're going to focus on is the idea that if we have exponential growth, we are going to use this function right here. Sorry, I need a marker there. That f of t, so the amount of people as a function of time, is going to be some constant times e to the power of kt. But what that constant is how many individuals are originally present. So what's our starting population? How many bacteria do we throw in the petri dish initially, or something along that lines? And one of the reasons why we use this function so much is that it does make taking the derivative a lot simpler. All right, so let's get right into actually using this equation. And it is important that it's different than what we used in Math 31 or 30-1, but that's okay. I am going to put up here that this is going to follow the function. This is really the amount of bacteria as a function of the time. Is going to be some constant times e to the power of kt. So it wants us to take this bacteria culture that starts with 2,000, and then after 3 hours, the count is 10,000. This is going to involve a fair amount of, using logarithms. Now, what we do know essentially is that f at 0 is 2,000 and f at 3 is 10,000. Now, one of these is, you're probably not going to have to do this work, but if f at 0 is 2,000, I'm saying that 2,000 is equal to some constant times e to the power of k times 0. That means that 2,000 is equal to some constant times e to the power of 0. So 2,000 is that capital C. Now, if you can remember that, you could certainly jump to that right away. I wouldn't have a problem with it. What we need then is we need the K value. So what I'm going to do is I'm going to use the fact that 2,000 is equal to C, but I'm also going to use the fact that f of 3 is 10,000. Because now I can say that 10,000 is equal to 2,000 times e to the power of k times 3. Now, I'm going to immediately divide by 2,000 to make this as simple as possible. I get that 5 is equal to e to the power of 3k. To solve this, what we do is we introduce the natural logarithm on both sides. On the right-hand side, the point of this is that the natural logarithm and Euler's number e cancel. And so I just get 3k. And when I divide by 3, I get that k constant is the natural log of 5 divided by 3. So the amount of bacteria we have after t hours is given by f of t is equal to 2,000 times e to the power, and it's a little bit ugly, but we're going to have that entire expression, ln 5 over 3 times t. You certainly will run into some fairly ugly, k constants. I would recommend that you keep them at least initially as their natural log form, and then as you get more and more used to these, you can certainly jump to kind of using your calculator a little bit more and putting in that decimal value. If you're going to use the decimal value, store it on your calculator. You don't want to just kind of truncate it at 2 or 3 decimals. You want to take as much accuracy as your calculator can give you. All right, to find the amount of bacteria after 2 hours, this is f of 2. That's going to be equal to 2,000 times e to the power of ln 5 over 3 times 2. And this is definitely just using your calculator. What I get is 5,848, just rounding to the nearest whole number. And there's that much. I guess it'd be bacterium? No, bacteria, right? Bacteria is the plural, I believe. Not a bio teacher. All right, find the rate of growth after 2 hours. Now, rate of growth is the derivative. This question wants f prime evaluated at 2. Right, f prime is the rate of change of f of t. So f prime at 2 is the rate of change of f of t when t is equal to 2. Now, in order to find f prime at 2, we have to find f prime. Now, I'm going to write that equation above. So f of t was equal to 2,000 times e to the power of the natural log of 5 over 3 times t. When I take the derivative of that, I'm going to put the 2,000 out front. I'm going to multiply. Now, the derivative of e to the power of x is e to the power of x. So e to the power of the natural log of 5 over 3 times t is still going to be there, but then I'm going to multiply by the derivative of that. exponent, and that is just the natural log of 5 over 3. This is why we worked on those exponential derivatives, because that is much, much easier to do, even though that's a little bit tricky still, than using, a base 2 or something along those lines. Base E allows us to do these derivative steps a little bit simpler. Not simply, but I would say a little bit simpler. All right, that means that f prime at 2 then is going to be 2,000, and I'll put the natural log of 5 over 3 in front here, but then I'm going to multiply by e to the power of 2 times the natural log of 5 divided by 3. And when I use my calculator, I get that f prime at 2 is equal to 3137, and the units would be bacteria per hour. And this is going to tell us how quickly that bacteria is growing. If we need it faster, maybe we need to increase the amount of food available or the heat or some other biological concepts that I might not have a good handle on. All right, last part here. When will the bacteria population reach 18,000? This wants us to solve when f of t is equal to 18,000, which I'm going to write as 18,000 is equal to 2,000 times e to the power of the natural log of 5 over 3 times t. All right, immediately, let's get rid of the constant. So we'll divide by 2,000. I get that 9 is equal to e to the power of the natural log of 5 over 3 times t. I want to get rid of that Euler's number, and I achieve that by taking the natural logarithm of both sides. And what I get is that, I'll write it over here to save some space, the natural logarithm of 9 is equal to, I'll write it out again here, the natural log of e to the power of the natural log of 5 over 3 times t. Well, the natural log and that e are going to cancel, so I get that ln 9 is equal to ln 5 over 3 times t. So I multiply by 3, I divide by ln 5, and I get my t value. Now, generally, we don't want to know it as 3 ln 9 over ln 5, so we would put that into the calculator, and what we get is that it's really, really close to 4 hours. Now, being able to predict how much bacteria are going to be there or how quickly they're growing is pretty important in a lot of different contexts. We have to get a little bit used to using these exponential functions because they certainly do benefit us in a lot of different ways.